Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics.
Welcome to Speaking of Reliability. This is Kirk Gray.
And this is Fred Schreckberg. Hey, Kirk.
Hey, Fred.
We got a question the other day.
Yeah.
And she said, she said, I'm relatively new to reliability engineering, and I've been asked to do a reliability allocation. And she explained it as just, as I think we all understand, is that we have a goal and I need to break it down to the main subsystems and to our vendors and stuff like that. What's an appropriate way to go do that? And there's, as you know, there's dozens of things in the literature on doing that, but I thought I'd bring this one up over to you because it's like, I doubt that you're going to go to the technical statistical processes to go do breakdown of the goals.
Well, okay, let's break it up into two different, mechanical and electrical. Okay, now with the mechanical systems, you do have consumable wear, bearings, things like that, where you can, or for electronics, batteries, lithium-ion batteries, and wanting to know how long before that's failing. The other side of, and with electronics, I don't know how you would say this, chip or whatever is going to be the first to fail, or allocating the reliability of each, circuit component.
People don't tend to do that. It's usually by the module, like a power supply, a hard drive, or motherboard, if it's a computer type system.
Right.
Or key components, if you've got a brand new technology in there and it's a brand new, MEMS sensor and nobody's ever used it before, you might want to have an idea if it's going to work or not.
Right. So the concept is that this particular, subsection black box has a limited life relative to what you need for the expected life of the product or expected user life of the product.
Yeah.
And so to me, that's, for electronic hardware, as we've talked about before, I have lots of electronics here that are 30 years old that are few electronics, like my pinball machine, and they're solid state logic and all this, in fact, fairly developed ICs back in the 80s.
Mm-hmm.
And they haven't failed. There's no limited life. Now, on the coils and the mechanics of what's called the solenoid and usually a plunger, or any of the mechanics, electromechanics, which are basically solenoid coils connected to mechanical linkage to the flippers. Now, those will definitely have a limited life in the fact that there's a sleeve of plastic or nylon around a rod, and it moves back and forth real fast, depending on how fast you play, and it warms up, it gets a little hot, and it may actually wear a little faster that way, but it does have a limited life. You're going to have, like a bearing or something like that.
I'll push back that there's plenty of electronics that have limited life. In a standard computer system or basic stuff, home appliance type stuff or entertainment systems, it's pretty benign. But put a chemical sensor system with communications in a drill rig that's right behind the drill head as it's 3 miles into the rock. It's lucky if it lasts for 2 hours. Right. And
I don't know.
It is. I've worked with those guys and that is, and it's $1 million pieces of equipment.
Right.
And if they get 2-3 hours out of it, or if they're lucky, they get a whole day out of it. They're like, oh, that's great. But that's it.
This is measurement while drilling?
Oh, yeah. They chemical sense. They have GPS systems in it. They have communication systems so they can talk to it. There's all kinds of weird, wacky stuff right behind the drill head. It's amazing. It's absolutely amazing technology.
Sure. But I've actually been through the factories and the engineers that tested, and I've talked to them. And one of them, at least he said, some of them last 4,000 hours. I was really
Yeah,
stunned
some
at
do.
that.
If they're drilling through sand, it's a piece of cake. You know, it'll last all day long. It really
Yeah.
depends on where they are and what they're doing.
Well, okay.
But other ones, like in the solar fields, they have great big customized IGBTs, and I don't remember what that stands for, but it's
Insulated gate bipolar transistor.
right, and they're pushing a lot of power through these things, and they fail. And there's two dominant failure mechanisms depending on how it's used.
Okay.
And you've run into other things that,
Yes.
like relays. That's mechanical connectors.
That's mechanical,
but
right.
Nobody claims fans. In their box, the mechanical guys say no, that's electrical. Electrical guys go no, it's mechanical, and then both end up blaming software.
Well,
but fans are a weakness in a lot of products.
Okay, right. Anything that's bearings, that's moving, that's a mechanical system.
Yeah, but IGBTs have no moving parts except electrons.
No, you're right. Okay, IGBTs do have a wear mechanism, and they do have limited life, and that's why.
So do light bulbs. They're electronic. They're electrical. LEDs, they wear out. There are no moving parts. They dim over time. They lose power.
Right, over time.
Yeah, that's a wear mechanism. There's no moving parts.
You're right. And I would give you, there are certain components that, especially in power electronics, that do have limited life, but they have to be, and they're learning more and trying to extend the life. But that's like in wind turbines, solar inverters, things like that.
The light bulb over your stove. It's,
well,
it's got a little more hot heat and humidity. It fails quicker.
We have such an evolution of lighting in the last 5 decades, 4 or 5 decades.
Oh, no, I agree.
Now that we're into LEDs, which are supposed to last forever, and you and I know they don't. In fact, I've changed light bulbs, but I kind of feel like that's probably some variation in manufacturing, not the actual LED.
Hey, it's still reliability. It's still not working for me. It's a limited life.
But somebody's trying to allocate that, saying, I know how much life this has in it. Okay. Yeah. For every application this thing is going to go through, I know how much life this is going to be. So I'm going to allocate, this is
X reliability to this one, and then we'll add them all up and multiply them all out.
Exactly.
But the idea, I think, is not just because some parts just really don't fail very often. A keyboard, for example, on a computer system.
Right.
You really got to do something horrible to it to make it fail. My daughter did. She poured a glass of milk on it, or tipped a glass of milk on it, and didn't tell anybody and didn't clean it. So then it got all this sticky, moldy green stuff coming up out of it. And it was like, I think that's gone now.
Right. And the hinge on a laptop, the hinge for the screen, that's gonna have a wear out mode. But that's again a mechanical system, just like any gears or motors or things like that. And a lot of it depends on the maintenance too.
It depends on maintenance and use and care and all kinds of stuff. But the memory of even solid state memory, it is pretty durable, but they wear out. There's all kinds of mechanisms that take out cells. And if you lose enough cells, it's not a functional memory chip anymore.
I guess I haven't observed that in the field or in my own computers, because most of it technological obsolescence. And I've got several laptops sitting around that, probably couldn't run today, but they're functional.
Back to the question though is, well, what's the method? And I could point to probably a dozen different, statistic based and optimize this and everything else. And I think that's really missing the point. And I think you're bringing up a part of it is that, one, you don't need to know a goal for something that's probably never going to fail. Don't worry about it. Drop it off the map.
Right, exactly.
Don't worry about it. But there are a few that either you just don't know. Let's say it's first time using an IGBT and you don't have experience with it.
Right.
Well, you should be suspicious of that just because it's new, and go learn about it a little bit. And you'll find out, in this application, it's probably going to be okay or not. Here's some models. Here's some estimates. Right. And if it's really close, you got to go figure it out and test it. Or you do halt, right? And you find something, you go, well, wait a sec, why'd that fail? And you get a mechanism and you go investigate it. How long will it last in our application? But I think that the idea is that you really need to narrow down the allocation to the vital few that you really need to invest in to understand or estimate or whatever. Keep an eye on other stuff for other surprises, but don't worry about the keyboard.
Don't worry about the keyboard. Don't worry about most ICs. Don't worry about anything that not power electronics, not moving. That for the most part. And we talked about, but batteries don't. Lithium-ion batteries don't have moving parts. They have chemicals
Right.
reactions.
Right. It's a chemical reaction, but they degrade with
But
their
you can only
ability.
reverse. You can only reverse that so many times.
They get
Right.
better, Kirk. They get better over time by generation to generation. But,
Right.
But lithium ion batteries have a finite number of charge recharge cycles in them.
Sure. Yes, and that's absolutely. I'm going to have to replace my iPhone battery because it's now 76% of its original capacity. And so,
how do you make a phone call? Wow.
Yeah, it's still pretty good, but
But the idea is that she was looking for, what standard or what technique or method, and I'm like,
okay,
that's really missing the point.
Let me ask some things. Wouldn't she have to know something about the physics of that mechanism that fails, that causes it to wear and eventually are fatigued till it fails, like an IGBT?
If you want to know, there's physics of failure models and accelerated life testing based on a failure mechanism. There's ways to get at it, but that's expensive, and that's sometimes not expensive. Known. Right?
Right.
So what if you?
So where are you going to go to find that?
Field data. Technical papers, just a flat out guess is better than just ignoring it.
The problem is you've got so many variables underlying that: the manufacturing methodologies, the use environment at the end, which will vary depending on the product. Certainly in portable products, it varies tremendously. So, how many times can you drop your iPhone before it will wear? Because it probably would,
Well, yeah, you and I both know that. We had daughters with phones.
Right, exactly.
Multiple phones.
And it's mostly the glass, though. That's the limiting life on, and the battery, glass breakage. Everything else in there, it's probably got more life. And I've got, I think we all have old phones sitting around that would power on, but
unfortunately, I'm covered under NDAs. I know too much about how phones fail, and it's not drop. That is an issue, but it's not the only one.
And it's not the battery.
And we were just talking about the other day is that it's I was talking to a group and it was, how do you model? If you're doing allocation, right? And you're saying, all right, we got a goal, and I'll use a simple example. You're doing a workstation. Okay. We got a motherboard, a power supply, memory, screen, keyboard, right?
Right. And
it's a series system, and we have some field data, and we got some new stuff. And what should it be? Well, I could go sit in the corner and go do a bunch of research and look up all this stuff and model it and analyze it and run a bunch of tests and come back and say, here's the optimum allocation for all these things. But it kind of really misses the point. So the question that I think when somebody sits down to do allocation, the real question that you need to be addressing is, well, what do we need to improve? What part of this do we need to fix to get better? Right.
Right.
And in a series system, there's only one thing that you need to get better. Well, which one is it? And if you already know that answer, what are you doing with allocation? You know what you need to go do.
Exactly. And, what is it and what are the limitations and why is that weakness there?
Yeah, and it might be technically you can't do that. If it's over 100 degrees, it's just never going to work. So,
and then maybe you have redundancy or something like that. I don't know. There's a whole bunch of ways, I guess, to compensate for that weakness, but to mitigate it.
And they cost money, whether design time or component cost or whatever. But I know you've heard this story before. It's this one group it was a workstation actually. And this guy created a very, very simple model that just said, here's the 5 major subsystems, and the staff was, each manager had a team working on one of the 5 major subsystems. And he said, well, we're starting this. How good is your design? What can you commit to that you're going to hit that reliability for it? And wrote it all down and said, if we all achieve what we just said we could achieve, we'll be 10% below our target for the reliability for this project. So we need to fix something. you know, and they looked at the power supply person who had the lowest estimate and said, I can only get to 85% or whatever the number was. And they said, well, what are the trade-offs? How much more would it cost? If you do redundancy, it doubles the price plus other complexities. If you buy a different power supply, a different vendor that has a different claim or capacity or whatever, come back next week with 3 options and 3 price points, and let's figure out how we can make this work.
Okay, Fred, when I've dealt with that, and I have been in product developments where they said, well, this component here is not got enough margin to last according to our calculations. It'll have a fit rate of something, and that means the whole design will not, the MTBF. And then, that's what they do. And I've actually seen them sitting in a meeting saying, well, you've got to change the value of that capacitor, because according to the Arrhenius, the 217 Arrhenius equation, this is the rate. This is what they use.
I know, but that's
you're
absolute
getting
bogus.
Into reliability. You're getting into reliability prediction.
No. You don't need to with allocation at all.
Okay. But you're having to say this is going to fail. This is a weakness.
Well, you do that in HALT. You say, hey, this failed. And it,
Oh, it's you see it empirically. You see that empirically. And then you take another sample. Does it fail at the same level? What does this mean as far as is the potential variation either in manufacturing or use environment?
Right.
And the distribution of these, the stress points.
It's a valid method to get a estimate. It's not
a time estimate. Not a time estimate.
I bet I don't really need a time estimate when I'm figuring out what I need to work on.
No, you need to improve it. You need to you say this is a weak part.
This is a weak part. We need to.
It has a very low right.
Yeah, we need to deal with that. When you're starting the design process, that's good enough. And then later you get to the spot where are we going to hit our targets or not? And then let's these 2 parts are the life limiting ones as far as we can tell. Well, will they make 5 years or will they make 10 years? Let's figure it out. But
figure it out. That's what I want to know. How do you figure it out?
Accelerated life testing is the most common one.
That's
using
expensive.
Field data.
It takes a long time.
It can be. But do you need the answer or not? If you really need the answer, you invest in it and you do it. And I've made my career doing that, running accelerated life tests for people.
But the biggest investment they should make is getting the field data back from the field, so that they know. And they don't do that. They generally some are better at
some are better at it others, but
depending on the expense of the equipment.
Well,
the value.
There's all kinds of variables on that, but it's also, I agree with you. It's invaluable information, and people tend to ignore it, and it gets siloed off someplace, whatever. But that's one method. Another is, and I've like the IGBTs. I work very closely with the vendors because they were very willing. Unlike you and I've talked about this before. Unlike many. They were willing to share. If you're using it this way, it's going to fail with this mechanism most likely. And here's our research on it. And here's the model. So you can adjust it to your application. Right. And they were very open and forthcoming going, here's how we know it. Here's how the evidence is. Here's our internal lab stuff. Here's our field data. Right. They were great.
Right. Because they're used in thousands of wind turbines and solar inverter panels, inverters, and
electric vehicles,
and stuff like that. Right. So it's one of the things that Cal's, I know, did a lot of work on, and mostly the most obvious prognostics and health management approach was that they looked for signals of degradation from the IGBT circuitry, and so that they could see the wear out curve. They could see that.
Yeah, I saw that, and it was all PhD level crap. And I like, let's put a thermocouple on this, and as this starts to heat up, we know it's in problem, and get ready to replace it. And it was way cheaper than what they were doing, and you could actually explain it to a manager, and they would go, "I get that," and you got to really understand.
Maybe that's another way, but that's a prognostic. Say the thing is getting warmer and warmer, it's becoming less efficient. And
like a motor, for example, in a factory, right?
Right.
Measure current draw. for the same load, same RPM, all that other stuff you're doing. If it's drawing more current to get that done, it's getting less and less efficient. You're going to lose. It's either brushes or it's in the coils. You got a problem. You got to keep an eye on that one.
Also, you could look at the vibration monitoring signal of that motor too.
And they do that for bearings to understand whether you got to replace bearings.
Exactly. Which would be two ways: the current, as the bearing wears out, it becomes more resistant. It requires a little bit higher torque. And then the vibration. Those would be two key prognostic indicators of decay.
There's
decline.
Also oil analysis. You take a sample of oil and look at how much metal's in it. And I mean, it's another way that people are using, especially in bigger systems.
But look how much variables there are in that, okay? The materials used in the bearings, the oil, the variation in the manufacturing, dimensional tolerances, all those are factors. And so you have to make an assumption that there's a narrow variation in that manufacturing process. And you may have more than one component supplier in that chain.
Well, that's a good point. And I found that oftentimes, especially if you're running a prototype and you get like 2 or 3 out of your batch of 10 had a problem with one component. I had that with a crystal, little metal can crystal.
Right. We've talked about crystals before.
Yeah. And
I've seen that too.
Yeah. And it was funny. I called the vendor up and I get a hold of one of their technical folks and I said, we were having problems with the crystal, kind of falling out of our circuit here. And I cut it open and he goes, wait, what? You cut it open? That's proprietary.
Yeah.
I'd use an X-ray, except it's a metal can. So I used I used a Dremel tool and cut it off.
All right.
And I said, I was amazed at how simple a crystal is. It's actually a crystal. It's a piece of crystal sitting on 2 little leads, tray kind of thing, like little springboards, like diving boards.
Right, because it's got to vibrate.
It's soldered to that. And it's soldered to it. And the side that cracked and created the open only had half the bead of solder didn't go all the way across. Mm-hmm. And he says, "You're not allowed to open that." Really?
Right.
What?
Yeah.
I can, so I did.
And we found one at Storage Technology where the mounting was too close to the side of the can, and through just a little bit of vibration, we could it would actually touch the side of the can.
Oh man, it's probably then a harmonic thing and cause a problem.
Right. So we saw that all they had to do is kind of modify their manufacturing process, and it worked fine. Yeah. But that's not a design. I mean, if you took the ideal crystal can and put that model in, you're not gonna account for the.
Well, that's why I don't say use it. That's why I don't say don't use these pure models, because I think that what you mentioned is that you're assuming the process is stable. And the number one thing to do with a vendor
and that's if you have one vendor, one supplier of that.
Oh, yeah. And
if you have 3, you're going to really
be all over the map. But for critical components, for essential things in your circuit, things that you really have no option on, or it's vital for the functioning of your system.
Right.
Don't worry about the allocation. Worry about getting the process stable first. Make sure that it's a stable, consistent process. Because I agree with you, is more often than not, that leads to problems. And they go, well, that's quality. And it's a failure in the field. And I don't care.
Yeah, that's 3 doors down. Go talk to him.
Yeah, that's too bad.
He's supposed to ensure the vendor is always making it perfectly centered.
Yeah.
Just like, SPC and what capability, what do you call it?
Capability analysis. That's actually can make more improvement for the reliability than most any other tool we got out there.
Right.
If you find it, like when you were doing HALT and we get 2-3 samples and they all fail at different places, same failure mechanism, but at different times, different stresses. Right. My first look is, what's the variability of this component or this subsystem?
Right.
Because that's often a real tell that it's not a stable process. And making a design change is kind of chasing your tail at that point. So anyway, let's get back to this question. Is the real idea is don't do 217 and MTBFs and fit rates and all that joker stuff. Is use the whole
How about
range of ways.
FIDEs? Oh, you got all kinds of prediction books to choose from.
I
So
know, but don't use any of those prediction books. Use the various knowledge that you got in the room and with your suppliers and vendors, the ones that are willing to work with you. And when you have to, break out the testing. But the essence is the allocation is not a product in and of itself. It's a way for the team to focus on what do we need to fix? What do we need to improve? How close are we to target? And you can use very rough estimates to start and go, yeah, well, we have a lot of experience that this is a problem. We need to work on it. Then go do that.
Right. Before you have the hardware, before you have anything built, yes, that might be something you do to, review the predecessor product or whatever and look at what the weaknesses were in that. And then try and mitigate those for the next build. But at the same time, once you first get the initial prototypes and hardware, that's when you start doing some stress testing, some life testing.
Yeah, you go find out what really is causing problems,
right.
And then you go fix those.
And see a little bit of the distribution in that design and the application of that component in the design, because that's a big part of it too, where the component is, how the component is used, whether it's going to be, and whether it's IGBTs, you could use many in parallel, which I think is what they do for very high power systems. And if you have a known mechanism in the IGBTs, based on what are the parameters, power, voltage, or the voltage, current, cycle times, things like that, then you could say, well, instead of 1, we need 5, and each one takes 1/5 of the load, or something like that. That would be in part of your design process that you would do before you built the thing itself. And then once you built the thing, you make sure, well, is the power to all 5 of those distributed equally? No, probably not. There's some variation in the circuitry. There's resistance. There's
it gets pretty complicated with that, because at the end of the day, when you're going from DC to AC, you got to get them all on the same phase.
Right.
And 5 different IGBTs will give you 5 different things.
Right. And if you're making, my drive recently to Texas, thousands of windmills, of wind turbines, rows and rows across the state of Texas, especially in the West. And I just think of how many in each one of those, also just changing those out, and when they're down, what it costs to go fix one. It's got to be a tremendous effort. You've got a big room on top of a huge pole. It's got all kinds of power electronics, plus the mechanics, and to get in there. And I'm guessing that the turbine companies know that these certain subsystems are going to have to be replaced. So they must make them. That would be another thing, is if you did find a limiting component or limiting technology, you would make it easily replaceable,
that's a theory anyway. that's probably a subject for another day.
Well, yeah, look at the iPhone battery.
Yeah.
Yeah. So, but yeah, that's another way to deal with a reliability weakness if you have it. If you can't do anything technologically about this is the fundamental limit of technology, then that's what you do and figure it out. So, allocation is probably something you do in the rough design stage, and hopefully you're actually using empirical knowledge of the field data. Again, hopefully you've collected and put the value of the field data in its proper place, which is very, very high.
It should be, yeah.
It should be fundamental, and because that really is when the rubber meets the road, is when the product is in its actual application and its actual environment, and shipping and handling and people's maintenance of it is a reality that you didn't account for, in your initial design phase. And you can't really see that sometimes with, the variation the customer is going to use it in, and making assumptions about how the customer is going to use it. And
Well,
assumption.
I'm going to have to update my answer to her. Just add the underlying assumptions of the various approaches and the manufacturing variability aspect of it. I didn't mention that in my first response to her. So
Okay.
that's kind of why we do this stuff is we get questions
Right.
and we get an answer back as quick as we can, but then we also chat about it and learn and go, oh, I need to update that answer or change it or whatever. So if you're listening to this and maybe facing allocation or maybe not, but what's on your mind? What questions do you have? As you know, in every one of these shows, we're always looking for, what your input is, what your questions are. And I find it a great conversation starter. That's why I'm always looking for them. That and if Kirk breaks another blender, we'll see how it goes. But if you've got a question or a comment on one of these topics or whatever's on your mind, you'd like to get some input on it, let us know. Head over to accendoreliability.com/go/SOR. You can find a couple ways to get in touch with us. Kirk and I and the other hosts of the show are available through LinkedIn, which we get a lot of the stuff I hear about often comes through LinkedIn, so it seems to be a good place to get in touch. But you can also email us and get in contact with us through the Ascendo site, through our About pages. So there's plenty of ways to get in touch. We'd look forward to hearing from you.
So much material you have, Fred. So many podcasts. It's amazing. You collected over the 7-8 years you've been doing this.
Oh yeah. I did get a compliment a couple weeks ago that somebody says, I'm grateful and impressed at the amount of knowledge that the Ascendo site has gathered. And they're like, oh, thanks. That's kind of the idea. It's the knowledge isn't any good unless somebody else knows about it. You can use it yourself, but that's pretty selfish. Let's raise the ship for everybody.
Yeah, and let's push the boundaries and push the knowledge. That's what I want. It's just, I don't want to. It's another Me Too place, that talks about better ways to calculate MTBF is not.
Yeah. Well, let's shelf this discussion for another episode.
Okay.
We're running pretty long.
All right.
Hopefully those people hanging out with us in their car can now rest assured we're going to close it up. So thanks, Kirk.
Okay,
we'll talk to you
Fred,
soon.
We'll talk to you soon.
Yeah.
Bye.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.